Welcome to today's class. So in today's class, we will look at two other common models for suspension analysis. These models will be used to analyze pitch and roll. Okay. So we are essentially going to look at a simplified version of a half-car pitch model that can be used to analyze the pitch motion. And then we will look at a complementary model for analyzing roll. Okay, so that's something we will learn in today's class. Of course, in the previous class, if you recall, we looked at the quarter car model, which is typically used for ride analysis. So we will today learn about pitch and roll analysis. So here we are looking at the vehicle from the side. So let's say the direction of travel, right, of the vehicle, let's say, is from right to left in this figure. Okay, so this is the front of the vehicle and this is the rear of the vehicle. Okay, so let's picturize it that way. And we are essentially lumping the entire vehicle using this mass M, and we take the pitch moment of inertia of the vehicle to be I. Okay, so that is the pitch moment of inertia. So now one approximation that we are doing is that we are going to neglect the unsprung mass effects in this particular derivation, and it's a simplified model since we are interested more in the natural frequency. So what we are doing is that we are also not including damping, but of course we can always include it later on if we require it. Okay, so that's something we are going to do. So if we look at the center of gravity, which is this, so Z of t indicates 1 degree of freedom. That is the heave motion of the vehicle. So that is the vertical displacement of the mass at the center of gravity. And then we assume that the front suspension is fixed to 0.1 and the rear suspension is fixed at 0.2 when looked at from the side. And Z1 and Z2 are the corresponding vertical displacements at the front and the rear suspension contact points. Okay, so we will see what they are. Phi t is the pitch angle of the vehicle. So we can have pitch angles, particularly when we brake and then or we accelerate, and even when we go on uneven terrain, the vehicle is going to pitch, right? So that's what we are going to look at. And K1 and K2 indicate the front and the rear suspension stiffness respectively. Okay, so that's what K1 and K2 indicate. And ZR1 and ZR2 indicate the road, vertical displacement profile at the front and the rear respectively. Of course, this the position, the longitudinal position of the center of gravity is indicated by L1 and L2. As usual, L1 plus L2 is going to be equal to capital L, right, which is going to be the wheelbase of the vehicle. Okay, so I hope all these terms are clear to us. Okay, so this half-car roll model, half-car pitch model is a 2 degree of freedom model. Okay, so 1 minute, sorry, something went wrong. Okay, sorry. Yeah, so this half-car pitch model is a 2 degree of freedom model. So what are the 2 degrees of freedom? 1 degree of freedom is the heave motion, okay, at the center of gravity, which is indicated by Zp. Okay, that is 1 degree of freedom. The other degree of freedom is the pitch motion, okay, phi t. All right, so those are the 2 degrees of freedom as far as the half-car pitch model is concerned. Now we are going to do some approximations to this model. Okay, so let us say we draw a very simple schematic of this mass M, which I'm going to draw here separately. Okay, so let me draw this mass M. So let us say, yes, please.
Sir, maybe before we can continue, yesterday the quarter car model, we were actually looking at only the heave motion, right?
Yes, yes.
Okay, so yesterday's model was 1 degree of freedom.
Okay, why was it 2 degrees of freedom? Because we considered two masses. Okay, both the sprung mass
Okay.
and unsprung mass, and we consider the heave motion of both the sprung mass and unsprung mass. Okay, so
Okay.
in
That's why
today's
it was
class,
2 degree of freedom.
2
Okay.
degree of freedom. Good question. In today's class, what we are doing is that so in fact, if we consider the unsprung mass in today's class, we will get a 4 degree of freedom model. Okay, the heave motion of the sprung mass, the pitch motion of the sprung mass, the heave motion of the two unsprung masses, right? The front and the rear, right? So that will make it 4. So the reason why we typically neglect the heave motion of the unsprung mass in evaluating the pitch motion are twofold. Typically, its contribution may be small when we consider the pitch dynamics. And second point is that if the degrees of freedom also increase, right, the equations become complex and we may lose out on some physical interpretation. Okay, so for that reason, we are making a simplification. I hope that is clear, right, sir?
Yeah, that's clear, sir. Thanks.
Yeah. Okay. Yeah. So now coming back to this diagram, let's redraw this mass. Yeah. Okay. So I am drawing this sprung mass uh, here. I think that was a good question because please note that in today's class we are only considering the sprung mass. Okay, we are neglecting the unsprung mass. Okay, so please let's keep that in mind. Okay, so let's say this is our mass and that dashed line is our initial position. So let us say due to the pitch motion, right? So let us say this is our vehicle CG, and about the vehicle CG, I'm just drawing an exaggerated diagram. Let us say the vehicle has pitched in this manner. Okay, so this is our axis of our vehicle, and consequently, let's say we indicate the, oops, sorry, 1 minute, 1 minute. Yeah, let's draw the same vehicle in this manner. So let us say I am going to draw the sprung mass in this manner. Okay, so once again, it's just an exaggerated approximation, you know, for us to uh, understand what's going on. It's not going to pitch by this angle. So what happens is that, like, if we look at this and let's say this is our pitch angle phi, okay, as a function of t. If we consider this point 1, right, so which is over here, of course it's going to go on an arc, right? But then, like, assuming this if you calculate this vertical displacement, right, of this point 1, right, uh, from this initial point, so oops, sorry, 1 minute, just give me a second. Let's say point 1 goes somewhere here and we want to calculate its vertical displacement. That's going to be equal to L2 sine times phi. Okay, I'm sure all of us can figure out why that is L2 sine phi, right? So because L2 is the moment arm, and then like phi is the angle of rotation. So L2 sine phi is going to be the vertical displacement of point number 1. Similarly, if we take point number, point number 2, sorry, this is okay. I made a mistake here. This is at the rear, right? So yeah, sorry about that. So let's say we consider point number 1, which is at the front, and let's say it goes like this. This displacement of point number 1 is going to be L1 sine phi. Okay, so I hope it is clear why it is L2 sine phi and L1 sine phi, right? So when there is a pitch motion, I think I have not drawn it to scale, so that's why it looks very odd. So please excuse me. Okay, so you can see that the length of the mass has suddenly decreased. I had to sort of shorten it due to lack of space. I hope that's okay. You know, like, or what I will do is the following. Just to be careful. Sorry, please give me a second. Let me just shrink it a little bit so that it appears more realistic. Okay, yeah. So consequently, what's going to happen is the following. So this, oops, this point, okay, so we are going to have this is our point 2, and that rotates and then like goes to L2 sine phi. Okay, so that's what it is. All right. So I hope that is clear. Okay, so consequently, what can I do? So if the middle point, okay, is going to be displaced by Z. Okay, this is the center of gravity of the sprung mass. Let's say the middle point is going to be displaced upwards by Z. We can immediately observe that Z1 of t without loss of generality, we are taking this counterclockwise rotation to be positive. Z1 is going to be equal to Z of t minus L1 sine phi t. Okay, that is Z1. And Z2, which is the vertical displacement at point 2, that's going to be equal to Zt plus L2 sine phi of t. I hope it is clear, right? How we got this. All right. So the Z1 is the vertical displacement at point 1. That's going to be Zt minus L1 sine phi. Okay. Why minus? Because we are going down, right? So if the pitch motion were in the opposite direction, it would be plus, right? But then like we are considering without loss of generality, the pitch motion to be positive in the counterclockwise direction. So that's why, we are essentially writing like this. So consequently, it is going to be the other way around, right? Wherein we are going to have Z2 to be equal to Z plus L2 sine phi t, because it's going to go up, right? So that's what is going to happen, okay? So these are the two displacement, right? At points 1 and 2. So now, what are the other things that we need to look at? Let us consider small angles. Okay, so we are going to make an approximation of small angles. So phi is going to be equal to is going to be very small. So if I make this approximation, we are going to consider sine of phi of t to be approximately equal to phi of t. Okay, so that is an approximation we are going to do. So if I consider that z1 of t is going to be equal to z of t minus L1 phi of t. Okay, this is once again an approximation, and Z2 of t is going to be equal to Z of t plus L2 phi of t. Okay, so these will be the equations for Z1 and Z2. Okay, so now in fact we will realize why we are considering the simplified model, right? So because we want to understand the physics rather than getting into a complicated mathematical equations that we will derive. Okay, so that's what we are doing. Now let's assume that the sprung mass has moved up and it was also rotated. Okay, so let me draw the free body diagram of the sprung mass. So it has rotated by some phi. It has also moved up or down by some z. Some heave motion z. Okay, so that is the sprung mass. So consequently, let us say this is the center of mass where the upward displacement is z of t. This is point 1, which is at the front where the displacement is z1 of t. This is at point 2 where the displacement is going to be z2 of t. Okay. Now, what will happen is that like we need to draw the free body diagram, right? So what are the forces that act on this sprung mass now? We will have the restoring forces due to the two springs. Now, if we consider the restoring force due to the spring with spring constant K1, the total restoring force will be K1 times Z1 minus ZR1, right? Why? Because the top end is going to be pushed up by Z1. The bottom end is going to be pushed up by ZR1. So the total stretch of the spring is going to be Z1 minus ZR1. So that's what we are going to have. Okay, so if we look at this free body diagram, the restoring force from the front suspension spring is going to be K1 times Z1 minus ZR1. Okay, the restoring force from the rear suspension similarly is going to be equal to K2 times Z2 minus ZR2. Okay, similar argument. So these will be the two forces that act on the sprung mass. So with these, we are going to write down the equations of motion for translation and rotation. So what can I write for translation? Why are we looking at translation? Because please note that there is one degree of freedom, which is the heave motion, right? That is the vertical displacement. So what I will get is the following for translation, mz double dot to be equal to minus k1 times z1 of t minus zr1 of t, okay, minus k2 times z2 of t minus zr2 of t. Okay, so that's what we'll have. Okay, so now what we do is that like we substitute for z1 and z2. So if I substitute for z1 and z2, I will have z1 to be equal to z minus L1 phi t plus k1. I'm just processing these equations, plus k1 zr1 t minus k2 z2 of t will be equal to z2 z plus L2 phi. All right, plus k2 zr2 of t. Okay, so that's what we'll have. Okay, so I'm just expanding. Now let's collect terms. Okay, I'm going to collect terms in a certain way so that like we are going to do pretty much the similar analysis what we did in the previous class as far as natural frequencies are concerned, right? So we will collect and write like this. So we'll get mz double dot plus k1 plus k2 zt, and then like plus k2 L2 minus k1 L1 phi of t, that's going to be equal to k1 zr1t plus k2 zr2t. Okay, so that will be the equation of motion for translation of the sprung mass. Okay, so this is equation, let's call it as equation 1. So this is for translation. Now we need to write a similar equation for pitch motion. Okay, so for rotation, for the pitch motion, what will happen? So once again, we write I times alpha equal to the torque. So if we go back here, so once again, we are going to consider small angles, right? So if we look at the perpendicular distance, it will be like L1 sine phi and L2 sine, L1 cos phi and L2 cos phi, but cos phi is almost 1. So we are essentially going to consider L1 and L2 as the arm distance between the arm lengths for these two forces. Okay, so that's an approximation we are going to do. So if we look at the torque due to the first force, it's going to be k1 z1 minus zr1 times L1, and the torque due to the rear suspension restoring force will be k2 times z2 minus zr2 times L2. Okay, so that's what we are going to have. So we will have I times phi double dot t to be equal to k1 times z1t minus zr1t times L1 minus k2 times z2t minus zr2t times L2. Okay, so this is what we have. All right, so if we simplify this, okay, I leave this to you as an exercise. Okay, so if we simplify this by substituting for Z1 and Z2, we will get I phi double dot plus K2 L2 minus K1 L1 times ZT plus k1 L1 squared plus k2 L2 squared times phi of t So please bear with me. It's a rather long equation. So that's going to be equal to minus K1 L1 Z R1T plus K2 L2 Z R2T. Okay, so this is going to be the equation of motion for rotation. And how did we get this equation of motion for rotation? Of course, from the above equation, we substitute for Z1 and Z2. Okay, so please note that that is an intermediate step. I'm leaving it to you as an exercise for you to do. Okay, so let's call this as equation number 2. Okay, equation number 2 is for the pitch motion. Okay, it's for the rotation of the body. All right, so now we simplify. Okay, we are going to put it in that matrix vector form like in the previous class. So equations 1 and 2 can be written as the following. Okay, so how can we write it? They can be written as M00I times Z double dot T, phi double dot T plus K1 plus K2, K2 L2 minus K1 L1. We are just what to say, bunching the terms once again, right? So we, by now, I'm sure all of us know how to do this, right? So we are essentially bunching the terms involving the accelerations and the displacements. So K1 L1 square plus K2 L2 square multiplying Z and phi. Okay, so this is the second equation. Sorry, second term in this equation. Okay, that's the second equation written like this. Of course, then we have the terms involving the road inputs, right? So I'm just going to write them here. So we'll get K1, K2 minus K1 L1, K2 L2 times ZR1T, ZR2T. Okay, so this is what we have. All right. So this 2 by 2 matrix is the mass matrix. Okay. This 2 by 2 matrix is the stiffness matrix. Okay. So we essentially want to do a similar analysis here also, right? So if we do a similar analysis, like where we solve for omega square, okay, then we get the natural frequencies associated with the uh, pitch mode, right? So we are going to do that exercise. Okay, of course, I'm going to pose the problem and then I'm going to leave the derivation to you as an exercise. By now we know how to do that, right? So we have done it for the quarter car model. So to determine the natural frequencies, okay, we need to solve determinant of minus omega squared m plus k is equal to 0. Okay, so this is the equation we need to solve. Okay, so in this particular case, what happens to determinant of minus m omega squared plus k? It becomes determinant of minus m omega square plus k1 plus k2. That's the first term. Then we have K2 L2 minus K1 L1. That's the second term. Then here also we have K2 L2 minus K1 L1. Then we have minus I omega square plus K1 L1 square plus K2 L2 square. Okay, and that's going to be equal to 0. All right. Okay. So of course, please bear with me. I think we are almost there. I am going to leave this thing as an exercise for you to solve, okay, because our motive is to look at a special case, what happens under a certain condition to these natural frequencies, okay? So, but please do solve for omega squared, okay? So, once again, you will get a fourth order polynomial in omega. You can, you with only coefficients of omega power 4, omega squared, and the constant term. So, you can solve for omega squared, right? Now, please do it as an exercise. Yeah, this is an optional exercise, okay? You don't need to submit it as a homework, okay? So, let us say we consider a special case where the pitch moment of inertia is the product of M, L, and T, okay? Right? Sorry, M, L, L1 and L2, not T, okay? Sorry about that. So let's say we consider the scenario where the pitch moment of inertia is the product of M, L1 and L2. So what are L1 and L2? If we recall, M is the mass of the sprung mass, right? L1 indicates the longitudinal position or the distance between the front wheel suspension mounting point and the CG, and L2 indicates the distance between the CG and the rear wheel suspension mounting point. Okay, so please remember that. So L1 and L2 are those measures. Suppose, let us say, the pitch moment of inertia is the product of M and L1 and L2. It so happens that you can do this as an exercise. You can complete this because the derivation is a little bit long. That is why I'm not doing it. I have come to this stage, and then like I'm going to leave this to you, the algebra to you as an exercise. So what we will see is the following. Just like, like yesterday or the previous class when we dealt with the quarter car model, here also we'll have a nice decoupling, okay? Wherein the two natural frequencies associated with the pitch model become square root of k1 by mf and square root of k2 by mr, where if you recall, mf is the mass of the vehicle supported at the front suspension, which is ml2 by l, and mr is going to be the mass of the vehicle which is supported by the rear suspension, okay, which is going to be ml1 by l. So what does this mean physically? If we have a condition wherein the pitch moment of inertia, right, is equal to the product of the mass of the vehicle and L1, L2, we get a nice simplification. That is, the two natural frequencies are decoupled, and it so happens that, like we can design the front suspension and the rear suspension independently, right? So because we can immediately see that the first natural frequency associated with the pitch mode is going to be square root of k1 by mf, which deals with the front suspension stiffness and the mass supported in the front suspension, right? So similarly, the second natural frequency associated with the pitch motion is going to be square root of k2 by mr, which is once again going to be the suspension stiffness of the rear suspension and the mass supported on the rear suspension. Okay, so we can see that there is a nice decoupling. Okay, so please do this as an exercise and convince yourself that this is the result. All right, okay. So this is a very neat result that comes out of the half-car pitch model. Okay. So any questions on the half-car pitch model before I pose the half-car roll model? So now let me pose the half-car roll model. I am going to leave the derivations of the equations to you as an exercise because I'm sure you can do that. It is just a similar process, but I'm going to explain to you what the model is. And then we will see a sort of like another model which is used to derive what is called as the static stability factor when we deal with the rollover phenomena. Okay, so we'll see what is the relationship between these models. Okay, so now let us say we look at the vehicle from the front or the rear. Okay, so that's where we are going to consider the roll motion. Sorry. Okay, so let's say we look at the vehicle and we look at the sprung mass. So this is our sprung mass. So now we look at the vehicle from the front and let us say this is our CG. Once again, we are going to have a heave motion. Okay, so which let's say we denoted by ZT. Sorry. Okay, let's say this is our heave motion. Let's say we call it as ZT. And let's say the left and the right suspensions are fixed at this point. And let's draw the two suspension springs. And they are in contact with the road. Okay, the road surface. So this distance, let's call it as some W. Okay, which is the distance between the left and the right suspensions. And assuming that it's symmetrical, these two distances become W by 2 and W by 2. Okay, so that is the distance along the lateral direction between the CG and the point of contact of the two suspension units. So let us call this stiffness as some KL, this stiffness as some KR. And let us say the displacement at this point, let's say we call it as ZRRT. And the displacement at this point, we call it as some ZRLT. Okay, L and R denoting the left and the right suspensions respectively here, right? So consequently, let's call the heave motion of this point to be some ZLT and the heave motion at this point to be ZRT. Okay, those are the heave motions at the left and the right points respectively, right? The contact points. So now, if you look at this model, this is also a 2-degree of freedom model. Okay, so this is a 2-degree of freedom model. We are going to have heave of the sprung mass and the roll of the sprung mass, sorry. The heave and the roll of the sprung mass as the 2 degrees of freedom. So heave ZT and roll theta T are the 2 degrees of freedom. Now for small roll angles, okay, once again we can get a relationship between ZL and ZR, right? ZL is going to be equal to ZT. We assume that the roll angle theta is this. Okay, so this is the roll, right? Because roll is the angle of rotation of the mass above the longitudinal axis, right? When we look at it from the front or the rear. So we consider the counterclockwise direction to be positive without loss of generality. And let's say the theta t is in this direction, right? If theta t is in this direction, ZLT, which is the heave motion of the left contact point, is going to be ZT minus W by 2 theta t, okay, for small angles. And similarly, ZRT, which is going to be equal to the sum of ZT and W by 2 theta t. Okay, so that's what happens to ZRT. Okay, so ZRT without loss of generality will be this, ZLT will be the previous expression. Okay, so I am going to leave this to you as an exercise. Please do this. So these are repetitive. Okay, so that's why I'm not doing this once again. So I want you to derive the equations of motion. So derive the equations of motion for both translation and rotation. Equation of motion for heave and roll. Okay, so you need to write mz double dot equals f, the net force, and I will be now roll moment of inertia, and then theta double dot will be equal to the net torque. Okay, so the forces that will come over, they will now due to the restoring force of the left suspension spring and the right suspension spring. Okay, so derive the equations of motion, put them in the standard matrix form, and then like calculate the natural frequencies associated with the roll motion. Okay, so we'll once again get expressions for this. Okay, so please do this exercise. All right, okay. So I hope this exercise is clear, right? So what I want you to do is like you essentially deal with this half car roll model. This is the formulation, and we essentially derive the two equations characterizing the translation motion and the rotation motion. All right, so that's something which we can immediately look at. Okay. So any questions on this before we look at the final topic, which is of rollover? All right. So let us now look at rollover. So rollover is when one of the wheels, right, lose contact with the ground, right, and the vehicle essentially flips. There is a risk of the vehicle flipping over, right? So we can broadly have two types of rollover. One is what is called as a trip rollover. Imagine that, you know, the way one, let's say we are driving in a car, and let's say one side of the vehicle, one tire hits an embankment or another projection on the road, and then due to that it trips over, right? So there are lateral forces, lateral accelerations that come about, and then like that's what is called as a trip rollover. So another class is what is called as the untripped rollover. So wherein we don't have, our tires are not going to hit any deformity or projections of the road, but then rather when I'm taking a turn due to the high lateral forces and the lateral accelerations, we are essentially going to have significant lateral load transfers that are going to result in the vehicle, one of the wheels losing contact with the ground. Okay, so that's what is called as a trip rollover. Sorry, untripped rollover. Okay, so let us now look at a very simple model that leads to what is called as a static stability factor, which is commonly used in rollover analysis, right? So let's see what the static stability factor is and how one can derive this. So let us say we consider this, we consider the vehicle and we are looking at it from the rear, right? And we essentially have the left and the right sides. And let's say, you know, like it's supported on some suspensions. And then like we are going to have the sprung mass, right, on top of the suspension. So for this analysis, what we are going to do is that like we are going to essentially neglect the suspension units. Okay, we are going to consider a rigid connection between the mass, the two masses, the sprung mass and unsprung mass. Okay, and then we will essentially do sort of like a lumped analysis. Okay, for simplicity. So this is a very simple model that is considered. Okay, so essentially what we consider is that like we consider the vehicle as one rigid vehicle, a rigid body, and then like we are going to do the analysis. So let us say the weight of the vehicle is concentrated here. Let's say that is the center of gravity of the vehicle, and let us say the weight of the vehicle is W. All right, and without loss of generality, let's say the vehicle is taking a turn to the left. Okay, so I'm sure all of us would have experienced this. Whenever we take a turn, right, what happens, you know, like we tend to roll out of the turn. Okay, so in a four-wheel vehicle, so consequently, you know, like if there is a chance of rollover, the inner wheels will lose contact, right? So that's what will happen. All right, so now when we are taking a turn, okay, so we are looking at untripped rollover. So when we are taking a turn, due to the forces that act at the tire road interface, there is going to be a lateral acceleration, as we have already seen from lateral dynamics, that's going to be generated. So due to this lateral acceleration of the CG, there is going to be this D'Alembert's force, right, which is going to act at the CG, and then like let's say that that's going to be W by G times AY. Okay, so that is the D'Alembert's force which acts on the at the lump mass of the CG. And let us say the height of the center of gravity from the ground, let's call it as some h, and let the normal load on the inner wheels and the outer wheels, right, be this be Wi, and let the normal load on the outer wheels be some Wo. Okay, and let us denote the width or the distance between the left and the right center points to be W, and let's call A and B as the corresponding contact point centers, right? Contact points. So, and since the vehicle is turning like this, there are going to be lateral forces which are going to be generated. So let's call this as Fyi, and the lateral force at the right wheel or the outer wheel, let's call that as Fyo. Okay, so this completes the free body diagram of this vehicle. All right, so I hope this free body diagram is clear. So we are going to do a pseudo-static analysis, right? So that's why we are essentially indicating the D'Alembert's force, right? So if we do this, and if we first balance out the forces along the lateral direction, if we write Fy equals 0, what's going to happen? We are going to get W by G times Ay is going to be equal to Fyi plus Fyo. All right. And we also know that W is equal to Wi plus Wo. Okay, so please remember that. Okay, so that is the balance in the vertical direction. Now, let us say we take moments about point B. Moments about point B. If I take moments about point B, what am I going to have? I am going to have Wi times W, that is one clockwise moment, plus W by G Ay times H, that is another clockwise moment, minus W times W by 2, that's going to be a counterclockwise moment, and this is going to be equal to 0. All right. So consequently, if we simplify this, we are going to get Wi, which is going to be the normal load on the inner wheel, is going to be equal to W by 2 minus W times Ay by H, sorry, Ay by G, okay, times H divided by W. Okay, so we are just simplifying these equations. So now, if we calculate Wo, which is nothing but W minus W by Wi, we are going to get W by 2 plus W times Ay by G times H by W. How did we get this equation? We use this equation. Okay, so that's it. Okay, so we used W equals Wi plus W. Okay, so on the other hand, consequently, Wo is going to be W minus Wi. Okay, so that's what we use. So we can see a similar impact coming in, right? So we can see this W by 2. So this W by 2 component in both these equations will indicate the static load. Okay, suppose there was no turn, right? No motion. So the load, assuming symmetry, is going to be split equally between the left and the right sides of the vehicle. But when we take a turn, what's going to happen is that there is going to be a dynamic load transfer taking place from the inner wheels to the outer wheels. So we had looked at longitudinal load transfer. This is lateral load transfer. Okay. So this is the dynamic load transfer along the lateral direction. So this is what is called as a lateral load transfer. Okay. So I hope this is clear. So we had looked at longitudinal load transfer. This is lateral load transfer. Now, when there is a risk of rollover, what's going to happen? When will the vehicle tends to roll over? When this inner wheel loses contact, right? So let's say I'm taking a turn to the left here, and let's say the inner wheel loses contact. What's going to happen? This entire vehicle may flip this way, right? So that is when there's a risk of rollover, right? So let's see what condition we get due to that. Okay, so when the inner wheel loses, contact with the road, okay, we have Wi to be equal to 0. So if Wi equal to 0, what do we get? We get W by 2 minus W times Ay by G times H by W equal to 0. If we simplify this, W and W get cancelled. So the critical lateral acceleration, okay, or the threshold lateral acceleration at which this rollover will happen is obtained as W by TH, 2H. Okay, so this is what is called as a static rollover threshold. Okay, so this is commonly used to evaluate how good the vehicle is to a rollover, right? So this is what is called as a static stability factor. All right. So commonly people will write it as T by 2H. Okay, we have denoted T to be T, what is called as a track, as W. Okay, so that's why we got the expression as W, but it's also denoted by T by 2H. All right. So what does this static stability factor indicate? You know, like it indicates what is the threshold lateral acceleration beyond which there is a risk of rollover. Okay, so that's something which we have obtained. All right. So, but in dynamic analysis, in fact, when we want to also like monitor, suppose we are able to measure the normal loads on the wheel, one can use what is also called as a lateral load transfer ratio to monitor what is happening as far as the rollover tendency of the vehicle is concerned in real time. Suppose we have the ability to somehow calculate the normal load on the left and the rear wheels, we can essentially calculate the lateral load transfer ratio as WL minus WR divided by WL plus WR. Okay, so we can immediately see that this ratio is going to be from -1 to +1. Okay, and what does -1 indicate? -1 indicates that WL will be 0. Okay, this ratio will essentially take the value of -1 when the left wheel lifts off. Okay, and this will take the value of +1 when the right wheel lifts off. Okay, when this becomes +1 when WR tends to 0 or WR becomes 0, right? So we want to ensure that we never reach -1 or +1. Okay, so if you want to do real-time control, you know, like if we are able to estimate this lateral load transfer ratio, we can maintain it as close to 0 as possible, right? Or small values, much smaller than 1. So that like we are able to decrease the chances of rollover. Okay, so but the most commonly used factor is what is called as a static stability factor. I wanted to show you how it is derived and under what assumptions they are derived, so that like we have a sense of what it indicates. So the static stability factor is nothing but a threshold on the lateral acceleration. Okay, so normalized in terms of G units, right? Beyond which there is a strong tendency for rollover. Okay, so any questions on our analysis of rollover? No. All right. So yeah, any questions? Yeah.
So this entire analysis, we have assumed mass to be negligible. Is it the amount of mass or weight of the unspun mass?
No, we in this analysis we have assumed the entire mass of the vehicle. Okay, yeah, it is lumped together. Okay, there is no suspension effects considered in this analysis. Okay, yeah. Yeah, so that is why I wanted to present various models. See, my motivation was that there are various models which are used, right? Yeah, so essentially when various models are used, that's when like we want to we get various results from it, right? I wanted to show you what are the finer assumptions behind those models. Okay, this T by 2H ratio is very commonly used, but I wanted to convey that this particular ratio is obtained under these approximations, right? We are going to lump the entire mass as entire vehicle as one mass, right? We are not going to consider suspension, deflection, and so on, right? So we are only going to consider what happens when the vehicle rolls as one unit. Okay, so that's what our focus is here. All right. So once again, see what I wanted to also articulate is that depending on the purpose, our visualization and the models which are used also vary. Okay, so that's something which I wanted to convey to you, right, through this analysis. All right. Any other questions? No. Okay, so yeah, if not, let me stop the recording here. I think with this, we have learned all the topics that we wanted to learn in this course on vehicle dynamics. So I thank you for your attention and all the best with further learning in this field. Okay, good luck.